Introduction to Hypothesis Testing, Chapter 10. Let's review some concepts. Which of the following bell curves represents an event that is most unlikely? Now in this class, shading the area of a bell curve indicated the probability of an event happening. So which of the following represent an event that is most unlikely? Which means small probability. Well, small probability is small area, so it's this one. Because if you look at the shaded area here, it's the smaller of all the shaded areas in all the other choices. So smaller area, more unlikely chance of something happening. Let's look at an example from practice problems I had assigned in Chapter 7. Pregnancy lengths are normally distributed with a population mean of 266 days and a standard deviation of 16 days. A woman claims that she got pregnant when her husband was home on leave from his duties in the Navy. She had a baby 308 days after his leave ended. What's the probability that a pregnancy lasts 308 days or more? So you should recognize in this problem that if you're provided with the mean and the standard deviation, you're going to be using the normal distribution, especially because it tells you it's normally distributed. You're going to be using the bell curve, and you're going to be using normal CDF to answer this question. The question does not involve a sample of so many women and the sample mean, so we're not going to be using the ideas of the sampling distribution. This is a problem that was taught in Chapter 7, and it's going to be a straightforward normal CDF problem using the standard deviation as the fourth input. So you're going to go to your calculator and you're going to enter the lower bound, which is 308 days, the positive infinity, or 100,000, because we say 308 or more. The mean is 266, and the standard deviation is 16. So I'll show you, just recap how to do this. Second DISTR, normal CDF, 308, 100,000. Mean is 266. Standard deviation is 16. And our probability is 0.0043. Remember that anytime a question asks for probability, and the question is referring to a normal distribution, you use normal CDF to answer the question. So 0.0043, if you convert that to a percent, it's 0.43%. This is a small percentage. This is an unlikely event. So when we consider the scenario that the woman was with her husband when he was home on leave, and then 308 days later she has a baby, the likelihood that the baby is the husband's is 0.43%. It's an unlikely probability. So we're going to therefore conclude that more than likely something happened while he was away on leave. Probably she was with somebody else, and the baby is not that of the husband's. The baby is some other man's child. And so that's what we did in Chapter 7. Now let's move on to questions from Chapter 8. Review of questions from Chapter 8. We have the population mean length of a pregnancy 266 and standard deviation 16 again. But what makes a Chapter 8 question different is the use of a sample, and the question is asking us for the probability that a sample mean is Okay, so take a look at the words. Suppose that a sample of 400 pregnant women is taken. What is the probability that the sample mean length of pregnancies is 268 days or greater? So you're trying to find the probability of a sample mean being 268 or more. So when you have a question involving the probability of a sample mean, you can't use the same method that you used in Chapter 7. The first step is finding the standard error. You have to recognize that you're dealing with a sample and you're asked for a probability of a sample mean being 268 or greater, so you should recognize that this problem involves the sampling distribution of means. So you have to find the standard error first. The standard error is going to be sigma divided by the square root of n. Sigma was 16, n is 400, so the sigma divided by the square root of n gives us 0.8. Okay, so you're going to do 16 divided by the square root of 400 on your calculator and you get 0.8. Little to no work has to be done for the mean of the sampling distribution because the mean of the sampling distribution is always the same as the population mean, and that's 266. So now when we go to normal CDF, our inputs are lower sample mean, that's the lower value, and then the upper value is going to be positive infinity again because it says or greater. The mean is 266 again, but this time the fourth input is not the standard deviation. The fourth input is the standard error, which is 0.8. So let's go to the calculator again. Lower 268, upper 100,000, mean 266, standard error 0.8. And we have 0.0062. Okay. 0.0062, which is 0.62%, which is also a very small probability. So this is a diagram of what we're after. In the center we have our mean and standard error. Remember that the sampling distribution of means is a collection of sample means. So all possible sample means are labeled on the horizontal axis, and the entire bell curve represents 100% of all these sample means. The sample mean in question for us is 268. The probability that the sample mean is more than 268 is the area to the right of 268. So the low value on the calculator is 268 upper 100,000. The mean is 266. Standard error is 0.8. And the probability of us at random choosing a sample of 400 pregnant women and having their sample mean be 268 days or more is 0.62%. So this should strike you as an unlikely event. The chance of us getting 400 women together and having this kind of result is 0.62%. Not a likely event. Okay, so now it's even 0.62 is even so small that it really isn't even shaded. It's almost impossible to see the shading on the bell curve because it's a real small probability. So imagine that you have 400 women. This is not 400, but imagine that we have 400 women. The probability of us getting this kind of result, if a sample of 400 women is taken, the probability that their mean pregnancy length is more than 268 days is 0.62%. Okay, so it's not likely that we can get 400 women at random and have their mean pregnancy length be 268 days or more. More than likely, if we randomly select 400 women, their pregnancy length is going to be somewhere in the middle, not far off on the right or far off on the left. There's a chance that it's far off on the right or far off on the left, because the bell curve represents probabilities, and there is a chance that some fall in the far right tail and some fall in the far left tail. But it's a small probability. So, keeping that in mind, what if this sample is special? Let's suppose that instead of those 400 women being randomly selected, let's suppose that all of them were taking a prenatal vitamin called Gestimax. This is a made-up vitamin. Gestimax, stay pregnant longer. So this is a totally made-up thing, but let's suppose that all 400 women were doing this. Does it appear that a long pregnancy is a result of Gestimax? Or could a sample mean of 268 days reasonably occur by chance? So we know that the chance of us randomly selecting 400 women and getting this sort of result, 268 or more, the chance of that happening is only 0.62%. So it could happen by chance, but the chance is very small. It's only 0.62%. So therefore, it's reasonable to believe Gestimax causes the length of a pregnancy to increase. The probability that an increased pregnancy length could happen by chance alone is too small to be reasonable. Okay, so that should seem pretty logical to you. It's such a small chance of getting 400 women together that have a pregnancy mean length of 268 or more. Because it's such a small probability, we're going to attribute the increased pregnancy length to the vitamin, because the likelihood of it happening at random is very, very small, too small to be reasonable.